HMS Starling, North Atlantic Convoy Route SC-122, March 1943, and Lieutenant Commander Frederick John Walker stands in the cramped radio room, watching his telegraphist operators hunched over their receivers, their headphones pressed tight against their ears as they listen intently to the crackling static that fills the high-frequency bands. The young sailor at Station 3 suddenly sits upright, his hand shooting toward the oscilloscope display mounted above his receiver, where a bright green line has just appeared, tracing a perfect vector across the circular screen that points directly northeast, at a bearing of 42 degrees. The transmission lasted exactly 8 seconds. Just a brief burst of Morse code, sent by some German radio operator aboard a U-boat somewhere over the horizon. A submarine commander reporting his position to Admiral Karl Dönitz's headquarters in occupied France, confident that his short message would be too brief for Allied direction-finding equipment to detect. But what that German U-boat captain could not possibly know, what German naval intelligence had failed to comprehend, despite more than a year of mounting evidence, was that the British had developed a radio direction-finding system so sophisticated, so instantaneous in its operation, that it could pinpoint the exact location of a submarine from a transmission lasting just 6 seconds. A technology the Royal Navy called high-frequency direction finding, but which every sailor in the Atlantic knew by its nickname, Huff Duff, a piece of equipment that would prove more deadly to German U-boats than any depth charge or torpedo ever could. The story of how Allied forces turned German radio communications into a weapon against the Wehrmacht begins not with some dramatic breakthrough or captured enemy equipment, but with the slow realization that emerged during the late 1930s that modern warfare would be fundamentally different from anything that had come before, that armies would no longer communicate primarily through written orders delivered by courier or through telephone lines strung between command posts, but through radio transmissions that travelled at the speed of light across hundreds or thousands of miles, allowing commanders to coordinate operations across entire continents in real time. The British military establishment understood this transition better than most, having spent the years between the wars developing increasingly sophisticated radio equipment for their armed forces, equipping everything from fighter aircraft to tanks to warships, with transmitters and receivers that could send and receive messages across vast distances. But a few forward-thinking officers at the Admiralty recognized something that most of their colleagues missed entirely, which was that every radio transmission was not just a method of communication, but also a beacon that announced the transmitter's location to anyone who knew how to listen, that the electromagnetic waves radiating out from every antenna carried information not just in their content, but in their very existence, in their direction of origin, and their frequency, and their signal strength. And if you could develop equipment sensitive enough and fast enough to capture those fleeting signals and determine where they came from, you would possess a weapon that could locate enemy forces without ever breaking their codes or intercepting their messages. A technology that would let you read not the content of enemy orders, but something far more valuable, the exact positions of the forces receiving those orders. The technical challenge facing British radio engineers in the late 1930s was that traditional direction-finding equipment required operators to manually rotate a directional antenna until they found the bearing where the signal was strongest, a process that took anywhere from 30 seconds to several minutes depending on the skill of the operator and the clarity of the signal. This meant that enemy forces could avoid detection simply by keeping their radio transmissions short, sending brief messages that ended before the direction-finding operator could complete his measurements and determine where the signal had originated. German military doctrine specifically emphasized this technique, training radio operators to compress their messages into the shortest possible format, creating what they called Kurzsignaler, or short signals, that conveyed maximum information in minimum time, messages that typically lasted less than 20 seconds when sent by an experienced operator. The Germans believed, quite reasonably based on the direction-finding technology they knew existed, that these short transmissions were essentially undetectable, that Allied listening stations might hear the messages but could never determine their origin quickly enough to be useful. And for years, this assumption proved correct, with British direction-finding stations struggling to get accurate bearings on German transmissions that ended before the operators could complete their measurements. The breakthrough that changed everything came from a Scottish physicist named Robert Watson Watt, the same brilliant mind who would later help develop radar, who realized in 1926 that you could eliminate the need for rotating antennas entirely by using a cathode ray oscilloscope to display the signal strength from multiple fixed antennas simultaneously. Watson Watt's insight was deceptively simple, but revolutionary in its implications. recognizing that if you connected two perpendicular loop antennas to the horizontal and vertical deflection plates of an oscilloscope, the electron beam would trace a line on the screen pointing directly toward the source of any incoming radio signal, with the direction indicated instantly the moment the transmission began, requiring no manual rotation or careful adjustment or time-consuming calculations. The system used what engineers called a Bellini-Tosi goniometer, a device that combined signals from multiple antennas in a way that produced a visual display where the bearing to the transmitter appeared as a bright line across the oscilloscope screen, with the angle of that line corresponding exactly to the compass direction from which the signal originated. The beauty of this approach was its speed, the way it transformed direction finding from a laborious process requiring minutes of careful measurement into an instantaneous visual display that any trained operator could read at a glance. A German U-boat captain might transmit for only 8 seconds, confident that his message was too brief to be traced, but a Huff-Duff operator, watching his oscilloscope screen, would see the bearing appear the instant the submarine's radio operator pressed his Morse key, would watch that bright green line stabilize on the screen for the entire duration of the transmission, would record the precise bearing before the message even ended. And if two ships equipped with Huff-Duff sets intercepted the same transmission, they could triangulate the submarine's exact position with an accuracy that would have seemed impossible just a few years earlier. The deployment of Huff-Duff technology across the Atlantic theatre followed a carefully planned expansion that began with shore-based listening stations scattered around the British Isles, and gradually extended to include shipboard installations on convoy escorts, creating a vast network of electronic surveillance that could track German naval movements across thousands of square miles of ocean. The shore stations were established first, with installations at Scarborough and Flowerdown near Winchester for the Royal Navy, at Chatham in Kent for the Army, and at Cheadle in Staffordshire for the RAF, each station manned by teams of operators who worked around the clock, monitoring the high-frequency bands where German military traffic concentrated. These stations were connected by dedicated telephone lines to central coordination centres, where intelligence officers maintained enormous plotting boards showing the positions of Allied convoys and known or suspected U-boat locations, updating these boards constantly as new Huff-Duff bearings came in from stations around the network. The system required extraordinary coordination, with operators at different stations timing their interceptions to the second, so that analysts could correlate bearings from multiple sites and calculate precise positions through triangulation. A single bearing from one station would show only that a U-boat was somewhere along a particular line extending out from that station, potentially hundreds of miles of ocean where the submarine might be hiding. But bearings from 2 stations would intersect at a single point, and bearings from 3 or more stations would provide confirmation and increased accuracy, allowing British naval controllers to plot U-boat positions with enough precision to route convoys around known concentrations of submarines, or to direct hunting groups toward targets of opportunity. The psychological warfare aspect of Huff-Duff proved almost as important as its tactical applications, because German naval officers operated under the fundamental assumption that their communications were secure not from interception but from location, believing that as long as they kept transmissions brief and random in their timing, the Allies could never track their movements through radio direction finding. Admiral Karl Dönitz, commanding the U-boat fleet from his headquarters in occupied France, built his entire tactical doctrine around the concept of the Wolf Pack, groups of submarines positioned in patrol lines across convoy routes, maintaining radio silence until one boat spotted a target, and then broadcasting that target's position so other boats could converge for a coordinated attack. This system required constant radio communication between the submarines and headquarters, with individual U-boats reporting weather conditions, fuel status, mechanical problems, sightings of Allied aircraft or ships, and most critically, the positions and courses of detected convoys. Dönitz's operations staff would receive these reports, plot them on their own massive charts of the Atlantic, and then broadcast orders directing other submarines to specific coordinates where they could intercept the reported convoy. The entire system depended absolutely on radio communication, on the ability of submarine commanders to report their positions and receive orders without being located by the enemy. And for the first 2 years of the war, this system worked brilliantly, with German Wolfpacks sinking Allied merchant ships faster than they could be replaced, threatening to strangle Britain's supply lines and potentially win the war through economic starvation. The installation of shipboard Huff-Duff equipment on convoy escorts beginning in February 1942 transformed the Battle of the Atlantic from a struggle where submarines hunted convoys into one where escorts could hunt submarines, turning the Germans' reliance on radio communication from a strength into a potentially fatal vulnerability. The shipboard sets were engineering marvels in their own right, designed to operate reliably in the harsh conditions of North Atlantic winter storms, where salt spray and heavy seas could destroy delicate electronic equipment. Mounted on platforms that compensated for the rolling and pitching of the escort vessel, so that bearings remained accurate even in rough weather. The technical problems of getting accurate direction finding from a steel ship with a complex superstructure that could reflect and distort radio signals were solved through painstaking calibration, with each ship undergoing extensive testing to determine how its own structure affected received signals at different frequencies, with correction cards provided to operators showing the adjustments needed to account for these effects. A Polish engineer named Wacław Struzinski, working at the Admiralty Signal Establishment, led much of this developmental work, solving problems that had seemed insurmountable to earlier designers. By early 1943, Huff-Duff sets were standard equipment on most escort vessels, with operators trained to watch their oscilloscope displays continuously during convoy operations, ready to catch any transmission from nearby submarines. The tactical employment of Huff-Duff by convoy escorts followed procedures that had been refined through bitter experience in the cruel mathematics of convoy warfare, where every decision meant the difference between ships saved or ships sunk, between hundreds of sailors reaching port safely or drowning in burning oil as their vessels slipped beneath the waves. When a Huff-Duff operator detected a transmission, he would immediately call out the bearing to the bridge, where the escort commander would plot that bearing on his navigation chart and make a split-second decision about how to respond. If only one escort had detected the signal, the bearing would show only that a U-boat was somewhere in that direction, potentially dozens of miles away, or possibly just beyond visual range on the surface. But if two escorts picked up the same transmission, they could triangulate the position and determine not just the direction, but the approximate range to the submarine. The standard response was what naval officers called running down the bearing, turning the escort vessel directly toward the detected signal and charging at full speed in that direction, hoping to spot the U-boat on the surface and force it to dive, disrupting its attack before it could get into position to launch torpedoes. An experienced Huff-Duff operator could estimate range from signal strength, judging whether the submarine was close enough to pose an immediate threat or distant enough that it was probably shadowing the convoy, waiting for nightfall to attack. This information allowed escort commanders to prioritize their responses, detach in ships to investigate distant contacts, while keeping the main screen around the convoy to defend against submarines that might already be in attack position. The German submarine force remained surprisingly slow to recognize the deadly effectiveness of Huff-Duff, continuing to operate under their pre-war assumptions about the limitations of Allied direction-finding technology, even as mounting losses suggested that something had fundamentally changed in the tactical balance of the Atlantic War. U-boat commanders dutifully followed their training, keeping transmissions brief and using their Enigma machines to encrypt message content, believing that these precautions made them safe from Allied electronic surveillance. Reports from submarines that survived encounters with convoy escorts described being attacked within minutes of transmitting routine reports, describing escorts charging directly toward their positions as if they knew exactly where the submarine was located. But German naval intelligence initially dismissed these accounts as coincidence, or attributed them to other factors like improved radar or better visual lookouts. Admiral Dönitz himself resisted accepting that Allied direction finding could be effective against his carefully shortened transmissions, arguing that the laws of physics made it impossible to get accurate bearings in the time available during a Kurzsignale transmission. He was technically correct based on the technology Germany possessed, which used the older rotating antenna systems that required longer transmission times, but he failed to understand that British engineers had developed fundamentally different technology that operated on completely different principles. The integration of Huff-Duff with other Allied intelligence systems created a comprehensive surveillance network that gave convoy commanders an unprecedented awareness of the tactical situation around their vessels, transforming convoy defense from a reactive posture, where escorts responded to actual attacks, into a proactive strategy, where they could detect and neutralize threats before submarines got into attack positions. The most important synergy was between Huff-Duff and Ultra, the intelligence derived from breaking German Enigma codes at Bletchley Park, with each system complementing the weaknesses of the other. Ultra could read the content of German naval messages, but provided no information about the precise positions of individual submarines, since those positions were encoded in map references and coordinate systems that changed regularly, and which often remained ambiguous even after decryption. Huff-Duff provided exact locations, but no information about the submarine's intentions or orders or fuel status, or any of the other tactical intelligence that convoy commanders needed to make informed decisions. But used together, these systems were devastatingly effective, with Ultra telling British naval controllers where U-boat patrol lines were being established and what their orders were, while Huff confirmed the exact positions of individual submarines within those patrol lines and tracked their movements in real time as they manoeuvred into attack positions or responded to new orders from headquarters. The combination allowed convoy routing officers in Liverpool